At long last. Hey everyone, thanks for showing up. Hope assignment 2 isn't giving you too many problems. Of course, due tomorrow, 4 p.m. or whatever it is. Today we're going to talk a little bit more, once again, not like going over assignments. We're going to go over some of my take on the course content. So we're going to talk a little bit about describing distributions, how to display them, and what sorts of things you should comment on when we're asking you to comment on a distribution. Having marked this a lot of times in the past, there's sometimes people who go into things like how normal it is or use terms like that to describe things. And I want to go through a little bit more what we expect you to say and kind of the sorts of things you should look for. And also this should work. There we go. So let's talk about the motivation first. Like I've said in other lectures or other tutorials, I guess, it's always great if you have something to go off of. So there's this reasonably popular website called peakbagger.com. It records mountains from around the world. It allows users to enter new mountains, submit track logs, say how many peaks they've gone up, and it's led to this kind of the term peak bagging, which is to go up as many of these named high points as you possibly can. With some web scraping and regular expressions, you can actually get all the peaks from this. I'm sure you could also contact the site administrator and get them, but if you know how to do the other stuff, it's a fun little project, and you can get this cool data set, which is all of the user-submitted peaks off of peakbaggers.com. So you'll note in this particular storage of the data, and we're not going to go into it too much, I haven't stored it as a data frame. It's actually just a list. There's a very particular reason for this that has to do with this data. And that's because a lot of mountains occur on borders between countries. So in this data set, if we go back to the different names, you can see that countries is one of the variables. Now that isn't unique for each peak. Because some of them are on countries' borders, it doesn't really make sense to count them as in one country or the other. If the summit is the dividing line, it counts for both countries. As a result, you can see here, a lot of these country entries have more than one country included. Some of them have 2, and very few have 3. I think actually, if you know the Matterhorn from like Toblerone, that one I'm pretty sure is 3 because it's right on the Swiss, French, and Italian borders. Now, addressing this multiplicity, you could do in a bunch of different ways. You could like just take the first of these, go alphabetically. You could try pasting countries together, add a flag for multiple countries. We're not going to go into that too much, but it's one of those things where you need to kind of decide what you're going to do based off of the analysis. So one of the key features of these peaks is its elevation, recorded in meters above sea level. This is kind of the main thing people are interested in if you climb mountains at all. Like Everest is famous because it's the largest numbers of meters above sea level. They determine this using like successive triangulation. So you start at sea level, you look to some point, you figure out how high it is, you go to that point, you look at the next point and figure out how high it is, and you keep doing that until you get to the base of a mountain. And you can leapfrog your way up to determine the tallest mountains if you want. Displaying these elevations seems like a nice place to start. So first, let's kind of take a look at what we're dealing with here. Just a very simple data check. We're looking at about 83,000 peaks. So that's the number that have been recorded on this PeakBaggers website. A couple of these are NAs. I've also done some filtering in advance of this. Essentially, because these are user-entered, sometimes people enter things wrong. And so even though the format of the page is the same, they'll enter in something which can't be read by R as an elevation, so you get these NAs. There's also a few different peaks which are recorded as not found or whatever else. And so you want to remove all of these, filter it out, just to make things a little bit easier to look at. So in total, we're dealing with 8,300 or 83,147 peaks. Now, the first thing you might want to do would be something like a stem and leaf plot. But with this many peaks, it would be basically impossible to display that in any reasonable screen size. So instead, if we want a fully granular display of the data, that is, if we'd like to see, all of the points, our only real option is a quantile plot, which I'm sure you've seen in class. So we have here on the x-axis the proportion of points below a certain point, and then we have the elevation in meters above sea level along the y-axis. A little title there telling you it's the quantile plot of all the elevations. Takes a lot to load these because it's 83,000 points, and R is pretty slow when it comes to doing a vector graphics display of that. So we might ask, what does this plot show us? Now, if you're like me, and you're used to reading quantile plots, it's pretty obvious what this plot shows us. You can say a lot about it. But of course, that's one of those skills you kind of need to train up in yourself. So the important thing to remember when you're looking at this is that determining density, or where most of the points are, is based off of the angle of the line. The flatter the line, the more points are there. The steeper the line, the fewer points are there. So we see here is one relatively flat section, which then goes up into a very steep section. That tells us we have this center kind of at lower peak numbers, maybe around 2,000 is probably where the center is, and then a very, very long right tail, heavily right skewed. And of course, you have some of those famous Himalaya ones like Everest right at the top. Of course, this also depends on the aspect ratio. Because this is something like an angle, the way you display the width and the height of the plot is actually going to impact how you see those different angles. If you recall from the lecture slides, we're most sensitive to seeing changes around 45 degrees. So you might try to play around with the aspect ratio to find where the plot gives you some great distinguishing features in areas you're looking at. It's going to take a second to load a lot of these plots, like I said. So here it is super wide, makes that line look even flatter than it did in the last one. When it loads, here is something that's a little bit flatter, or sorry, a little bit narrower, and narrower still, and narrower still. And I don't know about you, but when you make it a little bit narrower, especially in this one, I can detect some kind of changes in slope in this area that looked perfectly flat before. It almost looks like right here, it gets a little bit, you can see my mouse pointer, right? Yeah. It gets a little steeper for a section before flattening out again. Of course, however, if you take this too far, you basically lose the ability to distinguish pretty much anything. Like, I can't read a single proportion really off of that bottom axis, and it'd be really hard to figure out what to do there. You kind of lose a lot of the detail in the axis you're compressing. And so there is usually a sweet spot in terms of aspect ratio where you see the details you want to see and you haven't lost too much on either dimension. So what can we see from this plot? I already commented on it a little bit, but one of the things that I learned in my first year, I don't know if it's going to help any of you, but you never forget your socks. Shape, outliers, centers, and spread. This doesn't work for commenting on everything in statistics, but if you start by saying, what is the shape of the distribution? Are there any outliers or points of interest? What's the center of the distribution, and what's its spread? And you comment on those four things, that usually takes you most of the way through commenting on what a distribution actually looks like. So in this particular image, we can see something about the shape. Like I said already, you have something that's mostly unimodal. Maybe there's some secondary, slightly smaller modes. But there's a strong right skew, and that's that vertical point and that mostly flat point. Notable points and outliers. Well, there's this kind of cluster of peaks over there above 8,000 meters above sea level. I've dropped the axis labels here just because I want that to be like something to keep it in mind, but you don't need to read off of this one. There's this little cluster of points up there. Maybe not outliers, but certainly kind of notable because there's a separation between them and all of the other peaks, which seem to be almost a continuous line. The center of this distribution, there's a lot of different ways to do that. On a particular, or in particular in a quantile plot, the easiest thing to comment on is the median. You just look for the halfway point on the x-axis and find the corresponding point along the y-axis, and that gives you right away the median. Determining the mean, a little bit harder when you're looking at a quantile plot. It's not going to be quite as obvious what you should do to figure out what the mean is in this particular situation. The spread. Once again, with a quantile plot, it's very, very easy to read off quartiles or any percentile you might want. We can also see the entire range quite easily, which if you're using like a kernel density estimate, isn't the case because there's some extra weight that goes outside of the distribution. So seeing exactly where the peaks end is not so clear with something like a kernel density estimate. And these four qualities aren't always all you can comment on. You may see something in there that you're like, oh, this is really interesting. I should add a little note about that. You should always follow up on that and comment on those things. But like I said, the socks is always an important thing to remember. And if you comment on those four things, it usually is a very good start. And when you're commenting, just kind of say what you see or interpret what you see. So when I talked here about it being unimodal with a right skew, I saw a flat point and a steep point, and I interpreted what that means in terms of an actual distribution on the quantile plot. So because we can't really see any of the peaks here, like this is fully granular, all of the peaks are displayed, but because there's 83,000 points, it kind of just looks like a line. We can't actually see any of the peaks, so using a fully granular display, a display which displays every point, may not really be necessary. We might consider reducing this granularity somewhat by binning the data. And you saw this in the slides, this nice fun trick to turn a quantile plot into a histogram. I've added those boxes there to kind of evoke that memory. What you do is you divide the range into bins, you count the number of points in bins, and you can either display that frequency or scale it to give a density. But this introduces a few different parameters into our visualization. We have the bin width, first of all, that is, where do we do those breaks along the range? And we have the position of the first edge. I've put that in quotes here because if you go through the slides, there's this idea that the bins go eternally from negative infinity to positive infinity, in which case you're looking at something more like a phase, like a sine or a cosine, so like the phase of the distribution is what matters. But I'll call the first edge as like the one right below the first point. So we can construct a quantile plot automatically. All we need to do is order the points and then display the proportions on the other axis. But we need to choose these parameters when we're using a histogram. Of course, R is pretty good at hiding all of these choices. If you call hist elevations, you don't even need to think about what the bin widths are. You don't need to think about where the first bin is. R does all that automatically in the background. It has a whole bunch of rules that you can read about in the documentation that tell you what it's doing. But we can play around with this a little bit. The first thing we might try is varying bin widths. I don't know if I think this might be in the lectures, but sometimes you might see things like histograms that are displayed like this. So what I've done here is by using this quantile call, I'm using the deciles of this distribution as the breaks, taking the deciles of elevation, and I've got these 10 bins that result. It's generally a bad idea to do this. You can. Does anyone have any ideas as to why? Comments? Seeing no takers? What you've done essentially is you've confounded the height with the area of these different bins. Not only that, but we've done something where the resolution of the histogram changes over the range of the data. You see more bins where the data is more tightly packed, and you see fewer bins where it's less tightly packed. That means you might lose out on some interesting patterns in these less dense areas and focus too much on patterns in the bulk of the data. So you get this conflating of area, and you get this different resolution. And both of these also make it harder to compare between distributions. Because these bin widths aren't going to be universal, we need to choose them for every data set. If we choose them for every data set, then we try to compare two data sets. What ends up happening is you're going to have totally different bin positions for those two different data sets. You no longer have this kind of consistent measure of distribution that you'd like to be able to use to compare different distributions. So let's keep the bin width constant, value of h. So we can go back to R as default for a second. We can see some of the same features as we could see for a quantile plot. Keep in mind, these are estimating slightly different things. The quantile plot is kind of estimating the quantile function of the distribution, whereas this is estimating the density of the distribution. And the math that kind of does that transformation is in the slides, if you're curious to see what I mean by that. So we can see, once again, the shape is clear. We can see this skew. We can see this unimodality, as long as those maybe different secondary modes along the right side. Once again, the spread, easily determined. We can see the mean a bit more easily here. The idea for that is you look for kind of the balance point. If you have some sense of this being a solid shape, you imagine taking it out and putting it on a rock. Where would it balance is roughly where the mean is. But we've lost some of the details. We can't see outliers individually anymore. We can only see outlying bins. In particular, we can't see any points within the bins. We've lost all of that granularity. We've converted it into this count or this density within some parameterized thing we've decided. And it's also much more difficult to determine the quartiles. I mean, you could try to add up the different densities to figure it out, but it takes a bit more mental effort than just looking at where the line intersects. But the obvious improvement is the density here is obvious. Now it's encoded with heights rather than angles. And from Cleveland and McGill's tasks, we know that heights or lengths are going to be way better than angles at encoding something so we can determine it with accuracy. Like I said earlier, though, the bin placement matters for how this density looks. So we can try different break locations with the same bin width. And this introduces a new thing, which is like the step size. How many different divisions do you want to do within those bin widths?